From our perspective, a solar active region near the eastern limb is partly hidden by the curvature of the sun. We can observe it, but we do not yet have the same direct view of its magnetic structure that we will have after solar rotation carries it farther onto the visible disk. And magnetic structure is crucial. Solar flares are powered by magnetic energy stored in active regions. When stressed fields suddenly reorganize and reconnect, enormous amounts of energy can be released. The more complex the magnetic configuration, the more carefully scientists watch it for additional M-class or X-class flares. AR4513 has already demonstrated that it can produce M-class eruptions, and it is still moving into a better viewing position. This does not mean an Earth-directed catastrophe is coming. It does not mean the next flare will be stronger, and it certainly does not mean a major blackout is inevitable. Scientists cannot predict the exact time and strength of an individual solar flare with certainty. What they can do is monitor the region, measure its magnetic complexity as it rotates into view, track new flares, and determine whether future eruptions launch CMEs toward Earth. That is why the next phase may be more interesting than the first explosion. The M8.1 flare was a warning that this region has serious magnetic activity. The CME from this event appears to have missed Earth because of its position and direction. But as the sun rotates, the geometry changes. And when the active region faces us more directly, one crucial question becomes much easier to answer. How dangerous is its magnetic configuration really? Because the flare that already happened may not be the part scientists are watching most closely. The real story could be what AR4513 does next. The sun has just fired one of its strongest eruptions of the year, and the most important part may not be the flare itself. On August 20th, at 11:42 UTC, a newly numbered active region called AR4513 produced an M8.1 solar flare, just below the threshold for an X-class event. The eruption was powerful enough to trigger an R1, or minor, radio blackout over part of the sunlit side of Earth. And at almost the same time, the sun launched a coronal mass ejection, a huge cloud of magnetized plasma racing away from the solar atmosphere. But here's the strange part. The CME is not expected to hit Earth. It is heading mainly eastward, away from our planet. So there is no reason to expect this particular eruption to produce a major geomagnetic storm. But that does not mean scientists can simply ignore what happened, because the region that produced the flare is not disappearing. It is rotating onto the Earth-facing side of the sun. And that changes the story. AR4513 appeared near the eastern edge of the visible solar disk and quickly showed that it was capable of producing repeated eruptions. Before the M8.1, the same region had already produced an M1.0 flare on August 19th and another M-class flare on August 20th. After the M8.1, it produced another M-class flare later that day. In less than a day, this relatively new region had announced itself as one of the most active areas on the visible sun. The M8.1 event itself lasted from about 11:32 to 11:54 UTC, with the peak at 11:42. That number matters because an M8.1 flare is not just a bright flash, visible in solar images. Solar flares release intense radiation across the electromagnetic spectrum. X-rays can reach Earth in about 8 minutes because they travel at the speed of light. When that radiation reaches the upper atmosphere, it can disturb the ionosphere and interfere with high-frequency radio signals. That is exactly what happened here. The flare produced an R1 radio blackout over a sunlit region. For most people on the ground, this was not dramatic. But for high-frequency radio users relying on the ionosphere, even a short-lived disturbance can matter. And the eruption carried another warning sign. Radio observations detected a Type 2 radio emission associated with the event. Scientists use these signatures as evidence of shock waves moving through the solar corona. The estimated speed was around 1,201 kilometers per second. That is fast enough to tell us that the eruption was capable of driving a substantial disturbance through the sun's outer atmosphere. Then came the CME. Coronagraph observations showed a wide cloud of material moving mainly eastward. Current modeling indicates that it will pass behind Earth rather than strike us directly. The International Solar Weather Monitoring Community therefore does not expect this CME to produce a significant geomagnetic storm at Earth. That is the good news. But there is a second question, and it is the one scientists are watching now. What happens when AR4513 rotates farther toward the center of the solar disk? The most important question is no longer whether the sun can produce another powerful flare. It already has. The question is what happens when the same active region turns more directly toward Earth. AR4513 produced the M8.1 flare on August 20th at 11:42 UTC. It was classified at the R2 level for radio blackouts, and another M-class flare followed later that day. The European Space Weather Coordination Center reports that AR4513 was the most flare-active region during that period and showed growth in its leading spots. The Australian Bureau of Meteorology also expected R1 to R2 radio conditions through August 21st to 23rd because of the activity from this region. But the immediate threat from the August 20th CME remained limited. The CME associated with the M8.1 eruption was observed moving westward, but models indicated that it would pass behind Earth without a significant geoeffective component. In other words, the eruption was powerful, but its direction was wrong to produce a major geomagnetic storm here. This is where the geometry of the sun becomes critical. The sun rotates. As it does, active regions move across the visible disk from east toward west. AR4513 emerged near the eastern limb. On August 20th, its reported position was around north, 4 east 71. That means the region was still far from the central meridian, the point where an active region is most directly facing Earth. And that matters because a flare and a CME are not the same thing. A solar flare is an intense burst of electromagnetic radiation produced when magnetic energy is suddenly released. A CME is a much larger eruption of plasma and magnetic field. A flare can occur without a dangerous Earth-directed CME, and a CME can travel through space without striking Earth. This is also why the phrase, "the sun fired at Earth," can be misleading. The radiation from a flare reaches Earth whether or not the flare is pointed toward us, because the radiation spreads outward. But for a CME to strongly disturb Earth's magnetosphere, the cloud has to travel along a path that intersects our planet. The August 20th event appears to have missed that path. Now consider what happened in 1989. But there is an important difference between 1989 and today. Modern space weather monitoring is far more sophisticated. Scientists continuously observe the sun with spacecraft and ground-based instruments. They track solar flares, magnetic fields, solar wind, and CMS. When an Earth-directed CME is detected, models can estimate its arrival time and possible effects. Yet prediction still has a fundamental limitation. Scientists can often determine that an active region is magnetically complex and capable of producing strong flares. They can monitor its growth. They can identify a CME after it erupts and estimate its direction and speed. But they cannot reliably tell us the exact moment when a particular active region will produce its next major flare. The next few days, therefore, matter more than the next few minutes. For August 21st through August 23rd, the Australian Bureau of Meteorology expected R1 to R2 radio conditions, with C-class flares very likely and M-class flares possible. It also reported no Earth-directed CME observed at that time and said the August 20th CME was expected to pass behind Earth. That is not a forecast of disaster. It is a forecast of continued observation. In March 1989, a powerful CME reached Earth and triggered a major geomagnetic storm. In Quebec, Canada, the storm caused a widespread power failure that left millions without electricity for about 9 hours. It remains one of the clearest examples of how solar activity can affect infrastructure on Earth. But that does not mean AR4513 is about to repeat 1989. The comparison shows something more important. The direction of a CME can matter as much as the size of the flare. A powerful eruption can miss Earth almost completely. Another eruption from the same region could have a very different outcome if its trajectory intersects our planet. For most people, the immediate effects of a moderate flare are limited. High-frequency radio communications can experience interference on the sunlit side of Earth. Stronger solar events can affect satellites, navigation systems, aviation communications, and in extreme cases, electrical infrastructure. That is why scientists examine more than the flare's brightness. They track the magnetic structure of the active region, its position on the solar disk, the direction and speed of any CME, and the conditions between the Sun and Earth. AR4513 has already shown that it can produce M-class flares. As it rotates toward a more Earth-facing position, future eruptions will deserve closer attention. But there is still no evidence that a major Earth-directed event is inevitable. The correct response is not panic. It is observation,